Alex, can you share your screen?
Yep, just 1 second. All right, can everyone see my screen?
Nope.
Yes. Yes. Okay, perfect. All right, I'll go ahead and get started. All right, so I guess today I wanted to tell you about some recent work on how to convexify the epigraph of QCQPs. This is joint work with my advisor, Fatma Clinch-Razan at Carnegie Mellon. Okay, so I guess this first part will probably be review for all of you who were at Santa News lectures for the summer school, but I do want to go over it again just quickly. So I'll mainly be talking about quadratically constrained quadratic programs, or QCQPs for short. In this problem, you're given Q0, Q1 through Qm. These are quadratic functions mapping Rn to R. And I'm going to write each one as, I guess, a sum of a quadratic form defined by an A sub I matrix, a linear form defined by a B sub I matrix, and a B sub I vector, and some constant C sub I. And I guess in this problem, we're trying to find the minimum value of Q0, subject to the constraints that Q1 to Qm are each non-positive. Okay, so this is a very general class of optimization problems, and it captures things such as, I guess, max cut, or 0-1 binary programming, or even, I guess, general polynomial optimization problems can be reduced to QCQPs. Right, so pictorially, what does this look like? We're going to pick, I guess, I'll draw some pictures down here today for n equal to 2. So in this problem, I guess, right, in this example at least, we're picking some x from R2, where this gray shaded area is defined by, I guess, the Q1 through Qm constraints. And you have to pay, I guess, the value Q0 at that point x. So the first thing I'm going to do is I'm just going to play the usual epigraph trick. I'm going to introduce a variable t to move the objective function Q0 into the constraint set. And I'll let script E denote the x and t that fall in this epigraph. Right, this is just a usual epigraph. And I guess now that I'm minimizing some linear function over a set, right, this program, the value of this program does not change upon taking the convex hull of the epigraph. So pictorially, I'm moving from this blue epigraph to the pink convex hull. Okay, so I guess, you know, it would be really nice if we had a simple description of the convex hull of this epigraph, because then we could hope to find the value of opt, I guess, using like our convex, like tools and techniques from convex optimization that we have. So unfortunately, right, this is going to be probably a relatively difficult problem simply because QCQPs are NP hard in general. But I guess I'll be taking, I guess, like a alternate approach today. I'm going to start with a guess for what I think this convex hull should look like. And then we're going to try to determine some sufficient conditions that guarantee that my guess is actually correct. Okay, so I guess, right, so for this guess, I need to tell you about the standard SDP relaxation of a QCQP. So I'm just going to begin by rewriting the original non-convex QCQP. I'm going to introduce this new variable capital Y and constrain it to be equal to XX transpose. Okay, and then I guess because we have this access to this capital Y now, I can replace each of my original quadratic forms, X transpose AX, with this inner product, this trace inner product of A and this new matrix Y. And I'm simply going to relax this Y equals XX transpose constraint to the constraint that Y minus XX transpose is positive semi-definite. And I'll call the value of this program. So this program here, I will refer to as the SDP. I'll refer to its optimum value as opt sub SDP. Cool. And I guess I'll just play the same epigraph trick one more time. I'll move this objective function into the constraint set with this new variable t. Right, so I guess the feasible domain on the second line here consists of triples x, capital Y, and t. So pictorially, that's this region on the left here. That's this green, I guess, region that contains triples x, capital Y, and t. And right, we're looking for a guess for what the convex hull of the epigraph should be. And I guess the convex hull of the original epigraph lived only in the x and t variables. So I guess I'll just do the sensible thing of projecting this SDP epigraph onto only the x and t variables. Okay, so I'll let E sub SDP denote this projection in the x and t space. Okay, so that brings us to our motivating question, right? We want to understand what are some sufficient conditions that guarantee what we call the convex hull result. That is to say, when is it true that the convex hull of this blue epigraph, right, this pink set here, is given by the projection of the SDP epigraph, the green set on the right. So why you might care about this is that it automatically implies the SCP tightness result. That is to say, you can solve for the value of the QCQP using its SCP relaxation. But I do want to say also that the convex hull result is interesting in its own right, because you might have, I guess, imagine you had a very, very complicated problem, a complicated QCQP, for which SCP tightness did not hold, in which case, right, our sufficient conditions necessarily wouldn't cover it. But I guess even in that case, you might be able to find a subset of your constraints for which you can still apply the convex hull result. And in that manner, you could hope to successively relax your problem. And I guess this is something that's done in practice. Okay, so let me, I guess, quickly go over some of the related work. So there's a long line of work on deriving, I guess, simple descriptions of the convex hull of some non-convex sets. So as an example, I guess one line of work considers the case where the non-convex region is defined by a single non-convex quadratic function intersected with some number of additional constraints. So for example, Yodoran shows how to do this when the additional constraint is another non-convex quadratic. This interesting survey article by Buehrer in 2015 gives an overview of some of, I guess, the results up until this point, where the additional constraint is a ellipsoid with some number of linear inequalities. And as another example, Santana and Day show how to do this when the additional constraint is a polytope. In contrast to these results, I will not be making any assumption on the number of non-convex quadratics. Right, so some of the results I'll show you today will actually extend to an arbitrary number of non-convex quadratics. Okay, so I guess another line of work is convex hulls of mixed binary sets. So for those of you new to this, I guess it's relatively easy to impose 0-1 type constraints using a quadratic constraint. And so you can view, I guess, the work in this literature as showing you how to convexify highly structured quadratic sets. Okay, so in contrast to this line of work, I guess the results I'll show you today don't make any assumption on the structure of the quadratic functions, and we won't make any, structural assumptions on the quadratic functions individually. We will only be making assumptions on how they interact with each other. I guess there's also quite a few papers on SDP tightness, so sufficient conditions that guarantee the tightness result. So in this line of work, there are sufficient conditions for QCQPs that have, I guess, only diagonal quadratic forms, as well as QCQPs that arise in the context of quadratic matrix programming. I guess I want to say that our results extend a number of these sufficient conditions, and even in the case of SCP tightness, but also answer the more general question of the convex hull result. Okay, so let me just give you a quick outline for the remainder of this talk. So there will be 3 parts of this talk. In the first, I'll tell you about how to understand the SDP relaxation in just the X space. Okay, so usually we think of the SDP relaxation as being something that happens in the X and capital Y space, right? This matrix that we introduced to lift the original QCQP. But I guess, this trying to analyze it in the X and capital Y space can be a little difficult. And we show you how to actually understand it as something that happens just in the X space alone. Okay, and we will do this by analyzing something that we call the set of convex Lagrange multipliers. This is going to be a dual object that I will get to in a second. And then after that, I'll tell you about this notion of symmetry that we introduced for QCQPs, and we'll go through a couple of examples. And finally, I'll get to one of the corollaries of one of our results. This corollary is going to informally state that if the geometry of this dual object is nice, right? That is to say, the geometry of this set of convex Lagrange multipliers is nice, and you have a large amount of symmetry for some notion of symmetry, then you'll get both the convex hull result and the SCP tightness result. All right. So let's get started on the first part of this talk. So I'm going to tell you, I guess, a story that sounds very similar to, I guess, the usual story of Lagrange aggregation, right? So I have some vector, it's going to be my aggregation weights. They'll be non-negative. And I'm going to define this dual, I guess this Lagrange function, which is you can think of it as a function of both my dual variable gamma and my primal variable x. But I think for the most part, for now, I guess we'll just think of it as just a function of x, right? We'll think of gamma being fixed here. So for every fixed gamma, I guess I'll define q gamma x to be q0x plus the sum from I equals 1 to m of gamma I qi. And I guess the first thing to note is that this is going to be, again, a quadratic function, right? We're simply aggregating some quadratic functions with, we're taking linear combinations of a quadratic function. And its quadratic form, right? The quadratic form embedded in this quadratic function will be a0 plus sum from I equals 1 to n of gamma I a sub I. And right, so what we usually do is we say if we have a pair x and t from this epigraph set, that is to say if q0 of x is at most t, and qi of x are each at most 0, then obviously q gamma x is at most t, right? I'm going to think of this inequality, or I guess this implication as saying, if we fixed any gamma in Rn plus, then, right, if you consider the epigraph of q gamma, that is to say the pairs of x and t that satisfy this inequality on the right-hand side, then that set, right, this aggregated epigraph set, will necessarily contain your original epigraph set. Okay, so pictorially, I'm aggregating these constraint functions, these constraints, and I guess I get this green non-convex epigraph, or potentially non-convex epigraph. And I guess for any choice of gamma, right, these might be different aggregation weights, but for any choice of gamma, I'll necessarily contain the original blue epigraph set. Okay, but what we're really after is, I guess, valid inequalities for the convex hull of the epigraph and not the epigraph on its own, right? And unfortunately, even though q gamma x at most t is valid for this blue epigraph, you can see in both of these examples that this green epigraph does not contain the pink convex hull of the epigraph. Okay, and I guess the issue is that we're dealing with non-convexities here. Okay, so I guess a simple way to remedy this is to simply enforce that my epigraph, this aggregated epigraph, be convex, right? Because in that case, you contain the epigraph, the original epigraph, and so therefore you must also contain its convex hull. Okay, so I guess motivated by this, we're going to define capital gamma to be the set of non-negative aggregation weights for which the q gamma function is convex, or in other words, its quadratic form is positive semi-definite. Okay, and I guess our previous observation was that as long as you pick this gamma from the capital gamma set, the set of convex Lagrange multipliers, then this aggregated epigraph will necessarily contain the convex hull of the original non-convex epigraph. Okay, so pictorially that might look like this. Okay, and I guess, you know, up until this point, all of this sounds relatively straightforward, but I guess the interesting part about this, I guess this set of valid inequalities is that this is exactly what the STP does. Okay, we show that if you consider taking the supremum over little gamma and from the set of convex Lagrange multipliers, and you take the supremum of all of those q gammas, right? So recall that each of these is going to be now a convex function for gamma and capital gamma, and so this supremum will also be a convex function. We show that you can interpret the STP as simply minimizing in the original space, in the x space, this new convex function. Okay, and similarly, we can interpret the projected STP epigraph as just being the epigraph of this new convex function. Okay, so I guess this structural theorem shows us that if you want to understand the STP and you have a tight handle on how gamma behaves, then you can understand it and you can hope to do the analysis in just the x space. Okay, so, and I guess as a corollary to this result, right, when gamma is polyhedral, that is to say, when gamma has finitely many extreme points and extreme rays, this supremum is going to be defined by finitely many convex quadratics. And so this epigraph region will also be defined by finitely many convex quadratics. And I guess for those of you who know about, I guess, second order cones and second order cone representability, this, I guess, immediately implies that the projected SCP epigraph in the case where gamma is polyhedral, will also be second order current representable. All right. So I guess with that said, let me just show you some pictures of what capital gamma might look like for different instances of QCQP. So here I've drawn an example where capital gamma is polyhedral, and so I guess at the very least, this is, gamma being polyhedral happens sometimes, and I guess an important case that where gamma is polyhedral is the case where the AIs are all diagonal, right? Because in that case, this positive semi-definiteness constraint on this right-hand side is defined by dimension many linear inequalities, right? One for each diagonal entry. But I guess I also want to say that in general, this isn't going to happen, okay? Right, so let's move on to symmetries. So we define this notion, we call it the quadratic eigenvalue multiplicity. It's some parameter of a QCQP. It's going to be the largest integer k between 1 and n, such that each matrix AI, right, so these are the quadratic forms in your quadratic functions, such that each matrix A sub I can be written as a block diagonal matrix with k many, I guess, smaller hat A sub I matrices down the diagonal. Okay, and I guess as a first observation, we can always take k to be equal to 1. Right, k equal to 1 always suffices because we can always set I sub right, k, when k is equal to 1, this thing on the right here is just the 1-by-1 scalar, I guess. And we can always take hat A sub I to be A sub I itself. All right, so let's just look at some examples. Here's an example where I'll take n to be equal to 4. Right, that is to say, I'll take x from R4. So if you see, I guess, the L2 norm squared, right? So in R4, that's what this would look like. And you consider what matrix induces this quadratic form, right? That would be the identity matrix. You can think of the identity matrix as being a 1-by-1 block of a single entry 1 repeated 4 times down the diagonal, okay? The L2 norm squared, I guess, in general, will have k equal to n. And I guess this will come up again later in this talk. And I guess as a second example, right, if we had the second quadratic form, you can write down the matrix that induces it. And you can see that this matrix has this repeated 2-by-2 block twice down the diagonal, right? And I guess, like looking at this on the left here, you also notice that there's some sense of symmetry. And I guess this is, yeah, so I guess for this quadratic form, we would have k equal to 2. All right, so finally, I guess I can tell you about our results. So first, I do want to say that these are only, I guess, a corollary of one of our results. I didn't think I would have time to tell you about the full theorem. And if you're interested in the full theorem, you should definitely read the paper. But okay, so this corollary will say that assuming we have both primal feasibility and dual strict feasibility, if gamma, right, the set of convex Lagrange multipliers, is polyhedral, and k, the amount of symmetry, is at least the minimum of m, the number of constraints, and the number of non-zero linear forms in your constraints plus 1, then you will get both the convex Hall result and the SDP tightness result simultaneously. Okay, so I guess when you look at this, I guess the first thought is maybe that this is a relatively strict set of conditions, simply because I guess gamma being polyhedral and k being large are both relatively difficult conditions to come by. But I do claim that this corollary already covers a number of interesting cases. Okay, so the first case that this corollary covers is the case where m, the number of constraints, is 1. Right, so I guess for people who know about this and know, I guess, this area, the case where m is equal to 1 is known as the generalized trust region subproblem. That's, I guess, just a fancy name for it. But okay, so why does this corollary cover the case of m equal to 1? Well, gamma is going to be, right, gamma is the subset, is a set of convex Lagrange multipliers. And when m is equal to 1, this is going to be some set that lives in R1, right? And furthermore, it's going to be a closed convex subset of R1. And I guess, in R1, that's the definition of polyhedral. And right, so recall also that k will always be at least 1. And so this symmetry condition is also immediately satisfied for n equal to 1. Another interesting example that this covers is the case where your quadratic program does not contain any cross terms. That is to say that all of your a sub i's are diagonal, and in your constraints at the very least, b1 through bm are each 0. Okay, so in this case, right, gamma will be polyhedral because it will be defined by only the diagonal entries of the AIs, and k, which is always at least 1, will be right. It will be at least this second term in the minimization. And right, so I guess this says that as long as your constraints are centered around 0, then we can handle an arbitrary number of quadratic constraints. Okay, and this case is actually what I used to generate the pictures in the earlier part of this talk. Okay, and so I guess, you know, hopefully that convinces you that the second condition can cover some relatively, I guess, interesting examples. And I guess finally, this corollary also covers the case where the AIs are each multiples of the identity matrix, and n, the dimension, is at least m. Okay, so right, so in this case, gamma will be polyhedral simply because the AIs are diagonal again, and k, right, so the quadratic eigenvalue multiplicity. Recall that I guess for identity matrices, k will be equal to n, right? Because you can think of each a sub I as alpha I repeated n times down the diagonal. And so k, which is equal to n, will be at least n. Okay. So I do want to just illustrate this last case with a picture. So for those of you who,
Alex, you have about 3 more minutes.
Okay, perfect. Yeah, I'm about to wrap up. So yeah, so I guess for those of you who were at the EPCO summer school last year, you may recall this example. I think Sam gave this as an example. So I call this the Swiss cheese example. So you have some non-convex subset of Rn, and it's going to be defined by some number of constraints that enforce your set to live inside a ball, some number of constraints that enforce your set to live outside a ball, and some number of linear constraints. Okay, and your goal is to find the minimum distance from the origin to this non-convex region in high-dimensional space. So pictorially, that might look like this in 3 dimensions. Okay, and I guess the thing to note is that, right, because these are ball constraints, we can enforce all of these constraints using, I guess, quadratic constraints. The first type of constraints would correspond to a quadratic function with a quadratic form of the identity matrix. The outside ball constraints would correspond to quadratic constraints with the quadratic form -I, and the linear constraints would correspond to quadratic constraints with quadratic form 0. Okay, and right, so these are all multiples of the identity matrix. And so our previous corollary would state that as long as your piece of Swiss cheese were non-empty, and the number of dimensions you had to move in was at least the number of constraints, then the standard SCP relaxation is tight, right? So you could actually hope to solve for the value of this program. And I think this is interesting because it says that, I guess it extends, like, I guess, other conditions where now we're allowing our non-convex quadratics to interact with each other in meaningful ways. All right, so let me just wrap up. So we analyzed, I guess, this dual object gamma, and we said something about its geometry. And we introduced this notion of symmetry, this parameter k, which we were calling the quadratic eigenvalue multiplicity. And I claimed that as long as you have primal feasibility and dual strict feasibility, if k, the amount of symmetry, is at least these parameters in this table, then in the case of polyhedral gamma, you would get both the convex hull result and the SDP tightness result. Okay. In the paper, we actually proved a stronger, I guess, dependence on k. Right, we prove, I guess, this quantity here, which I guess I didn't show you guys because I don't have the time to define all of these terms, but I'll just leave it on this slide. We also have a number of results that extend the results from polyhedral gamma to more general gamma. But in this case, we do need a larger amount of symmetry, right? We need m+2 and m+1 respectively. I want to say, though, that we do have counterexamples to show that the same results do not hold in the case of general gamma. Okay. And that, so there's actually something interesting going on in the case of polyhedral gamma that allows us to take advantage of this symmetry. Okay, and our results also extend to equality constraints. So you can replace any of the inequality constraints in your QCQP with equality constraints, as long as you redefine some of the objects appropriately. And let me just conclude with some future directions. So I guess any sufficient condition for either of the STP tightness result or the convex Hull result will be, I guess, necessarily quite strict, simply because you know, these results, we don't expect them to hold for I guess super interesting classes of problems. So a good question is to try to understand whether or not we can relax our conditions if we relax our goal, right? If our goal changes to a approximation version of this result instead of STP tightness, and if we are only if we're satisfied with I guess some approximation to the non-convex value, can we relax our assumptions? Another interesting question is to ask whether the framework that we use to analyze this problem can be used to recover other convex Hull and exactness results in the literature. Yeah, and so I guess I'll end my talk there. I'll say that these slides are currently available on my website, and the full version of our paper is available on arXiv. And I'll take questions.
Thanks, Alex. We'll hold the applause again until after questions. Does anybody have a question? You can type the question into the chat box or just some kind of alert, and then we can unmute you. Anybody? I guess you answered all questions.
All right, sounds good. Cool. All right. Yeah. So, thank you. Yeah.
So yeah, if everybody could unmute, let's thank Alex.